Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy tutorials. In this tutorial we explain how to write a Python program and a ROS2 Jazzy Jalisco package from scratch for controlling a Turtlesim robot simulation. The simulation is shown over here. It represents a robot represented by this turtle that describes a circular trajectory. This turtle is a model of a 2D mobile robot. Its kinematics is very similar to a real robot. Over here you can see a Python script that's used to control the Turtlesim simulation. This Python script creates a publisher and publishes messages of the type twist. Messages of the type twists are actually command velocities. That is, we are controlling the velocity and angular velocity of Turtlesim simulation. Here for illustration, we have programmed a circular trajectory. However, you can easily modify everything explained in this tutorial to control any trajectory, or even you can modify this code to control the position of a mobile robot. Okay, let's start with implementation. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. If you have a Windows computer, then you can in parallel install Linux Ubuntu by using a dual boot option. To verify that you have the correct Linux Ubuntu version, open a new terminal by clicking here, then search for terminal, and then in this terminal type this command lsb_release-a, and as the result you should see Ubuntu 24.04. On the other hand, to successfully implement everything explained in this tutorial, you need to have ROS2 Jazzy Jalisco distribution installed on your system. If you don't have it, then go to my YouTube page and search for Install ROS2 Jazzy on Linux Ubuntu. There are several tutorials explaining how to do that. Let's verify that you have the correct ROS2 Jazzy distribution. To do that, we will list the content of the standard folder where ROS2 Jazzy should be installed, and for that purpose we should use this command, and if you see something like this, then most likely ROS2 Jazzy is installed on your system. Good. Let's continue. However, the best verification is to try to source the environment or to execute this setup.bash file. If you don't see an error, this is still a good sign, and then the final check is to try to print this environment variable, and if you see Jazzy, this means that ROS2 Jazzy Jalisco is installed on your system and you can continue. Okay, the first step is to install and start Turtlesim node and simulation. Most likely you already have Turtlesim installed on your system. However, it's still a good idea to try to install it just in case you don't have it. Before you install any program or a package on Linux Ubuntu, you need to run these two commands. Sudo apt update will update the package list or the package information, or better to say, it's going to refresh the package information on your local computer such that is up to date. And the second command will actually upgrade all the packages. So let's press enter, enter password, and be patient. Depending on how often you run these two commands, you might wait even for a few hours if you don't run it for a year, or you might wait 1 minute. As you can see, this command was immediately returned. This is because I'm updating and upgrading all the packages on a daily basis. To install the Turtlesim simulation for ROS2 Jazzy, you need to run this command. And then let's verify that Turtlesim is installed by listing all the executables. Here they are, and over here you can see several executables and programs that we have on our system. We are going to simply start the Turtlesim node like this. And now magic happens. You can see a new window is open and you can see our small beautiful turtle. However, we cannot move turtle. You can try to do that. Try to press any keyboard key and you'll see that nothing happens. So why is that? The reason for this is that we are not sending any control commands. Namely, Turtlesim simulation, or better to say Turtlesim node, receives control velocity commands through an appropriate topic. So let's investigate the name of the topic. Keeping this window open, or better to say this terminal open, click here. Then again, source the environment. And then type this command, ROS2 topic list. This command will list all the active topics. And you can see these two topics. These are the standard ROS2 topics. And you can see topics associated with turtle simulation. So what are topics? Topics are communication channels through which ROS2 messages are being sent. Messages are being sent from one node to another node. In our case, the node is Turtlesim simulation. That is, this is one node. And here is the topic that's used to send control messages. Namely, this node over here expects to receive messages through this topic. However, let's further investigate what are the type of messages that should be sent. For that purpose, run this command and you can see very useful information. First of all, we can see that this topic is communicating messages of the type geometry message, message twist. We can see that there are no publishers publishing to this topic, and we can see that there is only a single subscriber, and this single subscriber is actual Turtlesim node. Good. Next, we need to obtain more information about this data type, such that we know what we are sending. Now, before we do that, let's try to understand the kinematics of our robot. So, what is our robot? Over here, you can see a simple sketch representing a 2D robot, which is very similar to our simulation. You can see that the robot has two wheels and has bodies. We control the position, or better to say the velocity and angle of rotation of this node by spinning these wheels. Namely, if both wheels are spinning with the same velocity, the robot is going to move along the straight line. On the other hand, if this wheel spins faster than this wheel, then the robot will rotate. The kinematics of this robot consists of the velocity v and angular velocity theta dot. In the ROS2 literature, velocity v is usually called the linear velocity and theta dot is called the angular velocity. With the robot, we associate a coordinate system x, y, z. This coordinate system, which is a body coordinate system, is firmly attached to this robot and rotates and moves as the robot moves and rotates. This angle theta is the angle that the x-axis of this local body coordinate system creates with the fixed axis associated somewhere else. That is, this horizontal line can be an x-axis of a fixed coordinate system that's not firmly attached over here, but that's being placed over here. And this axis x is creating an angle of theta with the line that's parallel to that fixed axis. So this is the orientation of the robot. The velocity v is always in the direction of the local x-axis, and this is instantaneous velocity. That is, in a fixed time instant, velocity is always in the direction of x. On the other hand, theta dot, component of the angular velocity, which is also a vector, is placed or is projected along the z-axis. The z-axis points toward us, and you can see the tip of the arrow of the z-axis. That is, to control this robot or to control this simulation, we are going to send control commands v and the control command theta dot. That is, we are going to control the linear velocity and the angular velocity. So let's see what is geometry message twist. As you will see later in our code, geometry message twist contains 6 components. They're the components of the linear velocity vectors. We have 3 components, and these components are the projection of the velocity on the x, y, and z axis, and angular velocity vector. Again, angular velocity vector in the general case has 3 components, that is, it has projections of the x, y, and z axis. Since our simulation is in 2D, only the 2 components will be non-zero. They are the x projections of the linear velocity, denoted by v, and the z projection of the angular velocity vector, denoted by theta dot. That is, to control our robot, we are just going to control v and theta dot. The next step is to create a ROS2 Python package and node for controlling the Turtlesim simulation. Okay, for that purpose, let's close this terminal and keep the terminal in which Turtlesim is activated and open a new terminal. Then make sure that you navigate to the home folder. To implement everything, we need to perform 6 steps. In the first steps, we need to source the environment and create the workspace folder. In the second step, we need to create an empty package folder structure and required files. Then in the step number 3, we need to implement the source file. In step number 4, we need to modify the package XML and setup.py file. These are configuration files. Then in step number 5, we need to build the package and source the files by using the colcon build command. And in the final step, we need to run the velocity control publisher node. So let's start with the first step. First of all, source the environment. And remember, whenever you want to play with ROS, you need to source and underlay. Then, since we are in the home folder, we need to create 2 folders. Here we are creating a folder called turtlepy.ws. This is the base workspace folder, and inside of that folder we are creating the source folder. Next, since we want to build a package, let's navigate to the source folder, and keep in mind, whenever you want to create a package, always navigate to the source folder inside of the base folder. To create an empty package, we need to execute this command. The command is ROS2 package create. Then we need to specify what is the build type we are going to use. We are going to use Python, aim in Python, and over here we are specifying the name of our package. And press enter. Now, if you type this command, you will see that new folder is created. Then navigate to this folder, and inside of this folder you will see several files. Package XML and setup.py files are configuration files that we will modify. Setup.config is a configuration file that's automatically being populated, and we are not going to modify it. Resource and test folders are resource and test folders, as the name suggests, and we are not going to play with these folders. We will leave them as they are. However, you will see this folder, turtlepy package, and inside of that folder we are going to place our source file. So let's navigate to this folder. As you can see, it only has a single init.py file, and inside of this folder, let's create our source code. To create the source code, I'm going to use my favorite Python editor, which is Visual Studio Code, and I'm going to start it like this. If you don't have Visual Studio Code on your system, then you can go to my YouTube channel and you will find a video on how to install Visual Studio Code on Linux Ubuntu. And let's create the file. Click on File, New File, and call the file as demo.py. And here it is. Save it inside of this folder, and let's implement our node. Here, to save time, we are going to simply paste the content of the file, and let's explain this file line by line. First of all, we need to install, or better to say, to import RCLPY. RCLPY is the ROS2 client library for Python that is included with any standard installation of a ROS2 distribution. RCLPY provides the standard application programming interface, or an API for using ROS2 with Python. We are simply importing it like this. Then we need to import the node class. We do it over here. So what is a node class? Node class is a basic building element of ROS2 programs. That is, everything is implemented in a node class, or to be more precise, I cannot say everything. Most of the ROS2 functionality is implemented in a node 2 class. That is, to do something in a ROS2 world or in a ROS2 programming environment, you're going to instantiate an object of a node class. You will most likely define a publisher, you will define a timer, and then you're going to publish or receive some messages. Then we need to import the twist class. Twist class, or the twist data structure, or better to say a message type of the type twist, is the message that we want to send. As explained previously, twist is a data type structure containing components of the linear and angular velocity vectors that are used to control the 2D mobile robot. Next, we need to define the name of the topic that's used to send control messages. And here is the topic name. Note over here that I didn't invent this name. This name is precisely the name that you have seen while investigating the node. And this is very, very, very important. You need to always use the same topic. That is, this topic is the topic that our Turtlesim node expects to receive the message from. Okay, next we need to define the rate or frequency for sending the velocity control messages. Here we are sending 2 messages per second, and consequently I'm defining the rate messages. Here is our main function. Before using the RCLPY API, we must initialize it by using the init function. And this is the statement. In this statement, we call rclpy.init, and this should be done once per process. This function will initialize any global resources that are necessary for the middleware and client libraries. Next, we need to instantiate a twist message. I'm calling it control velocity. And then we need to fill in the components of the linear velocity vector and the components of the angular velocity vector of our twist. We simply do it like this. To create a linear velocity, we call control velocity.linear, and we specify x, y, and z. Here, as explained previously, I can only control my robot in the x-axis direction, and note over here that this is the body x-axis. That is, this is the axis that's firmly attached or fixed to the robot body and that rotates together with the robot. And here I'm specifying 2 meters per second, and over here I'm defining the angular velocity. Again, x and y components should be 0 since the kinematics of our object is constraining that, and only we have the angular velocity around the z-axis, and that's it. This type of motion will actually be executed in real time, and the robot will describe a circular trajectory. Then over here, we need to instantiate or to create our node. We call the constructor of the node class, and we specify the name of the node. I'm going to call it as a test node. Then we are creating a publisher. We call testNode.createAPublisher. We specify a type of the message that we want to send. It is a twist. We specify the topic name. Here it's where it's defined, and over here we specify the buffer size. Here the publisher object will publish our messages of the type twist. That is, we are going to publish control velocities. Here we create a rate to make sure that the messages are sent with a certain frequency specified by the rate message, and over here in this while loop we are sending the messages until rclpy.ok returns true. That is, until everything is fine and until we don't press Ctrl C, this loop will be executed. First of all, we print, send control messages, then we publish our control velocity, and then over here we call rcly py spin once, and we specify the node that we want to spin. This command will execute one item of work or wait until a timeout expires. Here we are not specifying a timeout, instead we are going to use rate sleep. Note that this is a non-blocking statement in contrast to the rclpy.spin, which is a standard command that you will find in other programs, and rclpy will spin the node and it's not going to proceed from this line. However, this will be executed once behind the scene. Here we put in a thread a message that should be sent, and then this command, or better to say this line, will publish this message, and that's it, and it will proceed further. Here we are sleeping or pausing the code such that we respect the frequency, or such that we ensure that the messages are sent with the desired frequency. And over here we destroy the node and we shut down, and that's it. And over here we make sure that we can call this script or call this function from a terminal, and that's it. Simple as that. Let's save this file and let's continue further. The next step is to properly set or edit the configuration files. First of all, click on File, open File, then go to this folder and open package.xml. And over here, we need to specify the dependencies for the build system. Namely, if you go at the top of the code, you will see that our code imports rclpy, and it's also importing something from geometry messages, and these are the dependencies. That is, our package depends on rclpy and geometry messages. rclpy and geometry messages are actually ROS2 packages, and they're installed together with ROS, and consequently here we need to specify these dependencies, or tell to the build system that our code depends on these two packages. Save this, then open a new file, then open setup.py, and over here we have to create entry points. Entry points are aliases or nicknames for our code. That is, we are going to use entry point names in order to run our code. The entry points should be set like this. So let me copy this. Then I'm going to erase this, paste this. Let me align nicely everything. And then let's put, oops, I made an error here. Okay, now it's good, and let's save this. So let's explain what's happening over here. I'm going to call the executable as publisher. So when I type ROS2 run package name publisher, this will be executed. We are going to go inside of our package, then we are going to go inside of demo.py file, and then we are going to execute the main function which is given and defined over here, and that's it. So when someone says ROS2 run name of the package publisher, we are going to actually run the main function from our demo.py file inside of our package turtlepy package, and that's it. So let's save this file and let's continue further. Now we are almost ready to build everything. First of all, go back to the original terminal and go to the base folder. You can go to the base workspace folder like this, or you can simply type something like this and you will be directly navigated to that folder. And keep in mind, whenever you want to build a package, you have to be in this base package folder. Keep in mind that, otherwise the colcon build command is not going to be executed properly. However, before building the package, make sure that you double check that all the dependencies are properly installed. For that purpose, install ROS2. Here enter password. Then initialize and update ROS2. You can simply ignore errors over here. And to verify that all the packages are, or all the dependencies are properly installed, you need to run this command. And as the result, you should see something like this. And if you see this, you can proceed further. To build the package, you need to call this command, colcon build. Then you need to specify package select, and then you need to specify the package name. That is the package you just created. Instead of writing all this, you can simply write colcon build. However, if you have like 10 packages inside of your workspace folder, all of them will be built. In this way, we are just going to build a single package and save time. Okay, and that's it. No errors, and now we are ready to run everything. To run everything, make sure that the terminal in which you started the Turtlesim simulation is active and that the Turtlesim window is also open. Then go over here, open a new terminal, and inside of this terminal you need to source an overlay. Sourcing an overlay means that you want to execute setup.bash file from the install folder inside of our workspace folder. That is, over here you're not executing the setup.bash file from the base ROS2 workspace folder. Instead, you're executing the setup.bash file inside the created workspace and package. So press enter, and now you can run the node. How to run the node? We use the command ROS2 run, then we specify the name of the package and the name of executable. Now the entry points might become more clear. So what does this thing mean? Okay, so what is publisher? Where is publisher defined? Well, if you go to the setup.py file, you will see that the publisher means execute from the package turtlepy.package from demo, that is from this file, the main function, and that's it. So let's run this, bang, and now we can see that we are sending control messages with a frequency of 2 Hz, and if you open the terminal, you will see how beautifully our turtle moves. Okay, that's all for today, and thanks for watching.